All right, so I guess we are live. So, welcome everyone officially to this review session where we want to sort of recap some of the material ahead of the second quiz. And just to reiterate, the topics for the second quiz are well, first of all, the topics that we already have for the first quiz. We'll have an opportunity to revise them. And then, other than that, the two new conceptual things are NP completeness and the notion of being able to approximate something in polynomial time. So those are sort of the two new topics. And for various reasons, we try to keep the video material around this a little light because these are sort of conceptually new things as opposed to previously all the other material was reinforcing things that you've already seen. So yeah, I think basically what I wanted to do by default was to maybe pick up some examples of ideas that we could recap. But before I try to um, impose a particular topic, let me just go around and ask if anybody has any questions, either from the materials or if you have any questions from the quizzes. And yeah, so we could start with that.
Ma'am, so in the review assignment two that you shared, so I
Yes.
just had a small doubt that one of the questions is options are seeming a bit not to make some sense. So if
Oh,
you can
really?
just
Okay. Maybe there is a typo or something. Let me check. So, can you remind me which question? Once again, it'll be really helpful if you can just share your screen so that I can look at
ma'am,
what.
actually, I think the date is not over. So and I
Okay.
mapped some answers. So
Oh, I see.
uh,
Okay. Okay.
yeah,
All right. So then, can you just tell me which question this is, and then I'll try to.
this is question number three from the review assignment number two.
Okay. Let me. Is this reducing independent set to set?
Yeah, yeah, I mean
Okay.
on those lines, yeah.
Right. So we're basically giving. Okay, so if I'm reading this correctly, we have a reduction which starts from an instance of independent set and tries to construct an instance of SAT based on the independent set instance. Correct? That's the premise of the question.
Yes, ma'am.
Okay, right. So, okay, I'll read out the options that I have, and then after I'm done, you can confirm if those are the options that you see, and then we can discuss if they make sense or not. Okay. All right. So let me just read out what I am seeing here. It's possible that already what I'm seeing is that maybe there's a formula that's missing, but okay. So the question is basically, does the reduction work? And the first option says it's not correct because it might produce a satisfiable formula for graphs where the largest independent set has fewer than b vertices. So that's one of the options. Another option is that it's not correct because it might produce an unsatisfiable formula for a graph that has an independent set of size b. The third option is that it is not correct because it does not run in polynomial time. And the fourth option is that the reduction is actually correct. So these are the four options. Do you see these four options or do you see something else?
No, so for the first and the second option, that B letter is missing. So that
Oh,
is
I
why it
see.
was
That
not
may have
making
caused some
sense.
confusion. I see. I see.
Yes.
Okay, so I think on the PDF that I have generated, the B is there, but it's kind of really tiny for some reason. I don't know. Maybe there was a rendering issue, and that's what went to the team. So it's possible that it was either not understandable or missed. So anyway, the point is that we are saying it's not correct either because it maps a yes instance to a no instance, or a no instance to a yes instance. Both of those would be incorrect things to do. So I think the first one is saying that okay, that there is no independent set of size b or more. So it's a no instance, but you produce a satisfiable formula. So you're producing a yes instance. So you're going from no to yes. That's the first option. The other one is saying that well. you might get an unsatisfiable formula even though you started with something that has an independent set of size b. So you're going from a yes instance to a no instance. So if that potentially happens with a reduction, then that reduction would not be correct. So basically, we are trying to understand why the reduction is not correct. I think it's been given as a MCQ, which is already kind of probably a bit of a giveaway. I mean, potentially both of the first options could have been correct, but in this case, I think we already know that if at all, at most one of them would be correct. And the other issue you might have is that a reduction may run. Um, the running time of a reduction may not be polynomially bounded, so that could be yet another issue. So you might preserve the equivalence of the instances, but an issue could be that yeah, you basically yeah, you've overshot in terms of time. So I'm just trying to see what would be an obvious example of such a reduction. So for instance, if you're doing the same thing from independent set to SAT, but I'll say that, well, let me generate a clause of SAT for every B-sized subset of the graph, right? And I have this kind of funny looking SAT formula. It will not exactly be in CNF. We can convert it to CNF later. But basically, I want to know, is any one of these B-sized subsets sort of an independent set? So maybe I'll have a clause for each one of those sets, and the clause becomes true if and only if those B vertices correspond to an independent set. So basically, you can design such a clause. I think that's an easy thing to do. But the point is that you will have a clause for every B-sized subset of the graph. So that is the number of clauses you are generating is n choose b. So even to write down your formula, you need n choose b time, right? Because your formula's length itself is going to be n choose b. But n choose b is, for some values of b, can be exponential in n, right? If b is a constant, it's okay. Like if b is 2, 3 or something, n choose b is like n squared, n cubed, and so on. So you're fine. But if b is like n by 2, for instance, then n choose n by 2 is actually exponential in n. So you have to be careful. So a reduction which is like that, so I did not fully specify the reduction, just sort of gave you a sketch. But if a reduction is like that, that would be an example of a reduction which which requires exponential time, and therefore it would not be a valid even though it maintains equivalence. So you can complete the details of this reduction so that yes maps to yes, no maps to no, so you get proof of equivalence quite easily actually. But it would still not be a valid NP completeness reduction. Like you cannot argue the NP completeness of anything from a reduction like this one, because it doesn't even run in polynomial time. And this is something we had discussed at length last time, so hopefully this example makes sense. But anyway, yeah. So basically, the short answer to your question is that if the letter B is missing, then please keep that in mind, and I think we should send an announcement out to highlight this fix. So thanks for pointing that out, Arya. Any other questions from anyone from any of the materials that we have so far?
No.
Ma'am, so can we discuss a bit more about these non-polynomial time reductions? Because that is a bit confusing. For especially like in this question, I'm not fully like this thing very
Okay,
comfortable with it. So
so in this question, would it help if I maybe try to explain what the reduction is doing?
I mean, maybe for a question it is fine, but like in general, if we can just get an idea as well, like when does it become non-polynomial time? Because even the examples you gave right now, those were also like I did understand bits of it, but not fully. And I think you took one of the examples in the videos, which was I think the subset sum, wherein you do the opposite reduction, right? Sorry, from the independent set to the subset sum, sorry, subset sum, yeah. So
Um,
not in, so then that is when you said that it would be pseudo polynomial because the number of bits used to store increases. So then, so That was
Right.
a bit confusing. So
Okay, sure. So, yeah, so maybe let me see if I can do a slightly sort of a relatable example, but I'm going to see if this time at least um, I've installed Google Meet on my tablet, so hopefully I'll be able to join. Let's see. It's been a little tricky doing these explanations in the air, so let's see if I can share my screen. That would be nice.
When you told something, I missed it, the last line.
Um, Yeah, sorry. I'm just trying to. I think I'm just waiting to be let in. I think. Yeah. Okay. So let's see. Okay. So I think this works. We just try and create a space where I can write. Sorry. Was there a question?
No, ma'am, nothing to myself.
Okay. All right. Sure. So let me just. Okay. So okay. So hopefully you can see my screen now. Just give me a +1 in the chat if you can. Okay, great. So, by the way, I think I do remember Arya's question, and we'll get to that in a minute. But while we are here and while everyone's around, let me just take the next few minutes to do a quick overview of the topics that are involved, just so that um, you have that in memory as you start. I mean, I'm sure you're already preparing for the quiz, but just to recollect, we sort of started off with greedy algorithms, and then we went on to this notion of matroids, um, and then we did some dynamic programming, and then we did flows, which was our first introduction to this notion of a reduction, because we also did applications. So we saw reductions here, and then we really saw a lot more about reductions when we started talking about NP completeness, and the final topic is approximation. So, in terms of sort of the main ideas involved with greedy algorithms, for most optimization problems, you can usually come up with some sort of a greedy looking strategy, because something is going to naturally feel optimal depending on what you want to optimize, right? So, the main challenge with greedy algorithms tends to be to show that whatever ideas you've come up with is actually optimal. So I think a classic example of this sort of thing is this coin change problem, where you say that, well, you have coins of certain denominations, and let's say you want to make n rupees using the smallest number of coins, and you'll be tempted to say that, okay, take the coin which has the largest value that is still smaller than n, right? And so for example, let's say you want to make 49 rupees or something like that, and uh, let's say you have you know 10 rupee coins, I don't know, 3 rupee coins and 1 rupee coins or something like that. And so what you might say is, okay, I'm going to start off with 10 rupee coins for as much as I can, because that's the maximum mileage that I'm going to get, so I'm going to use 4 of those. And now I can no longer use 10 rupee coins because I'm left with 9. So I'm going to use 3 rupee coins instead. And in this case, you can perhaps argue that you really need 7 coins. You cannot do any better than the greedy strategy. But by tweaking these examples a little bit, so it's basically when you see things like this, you're very tempted to believe that yes, if you do the greedy thing, if you try to locally maximize whatever it is that you're trying to, or locally optimize, in this case you're trying to minimize the number of coins, so you locally push for optimizing your final goal, then things should work out. But I think as we have seen in the videos and elsewhere, hopefully, this sort of intuition may not always work. So with greedy, really the most crucial thing is to be very careful about setting down and proving the correctness of your approach. Now, I think we've heard before that, well, I mean, for an exam problem, you might just, go with your gut feeling, and you may not have enough time to actually prove your algorithms to be correct. And you might do some like case analysis and trial and error to convince yourself that at least on that example it worked. Like here we did one example and it seems to work. So that's fair. I think it's fair game if you're in like a time limited setting, but I definitely encourage you to at least go back and really confirm that your ideas were, can actually generalize and you can get a proof. Or see if you have counter examples and then think about either alternate greedy algorithms or maybe just a different approach altogether, right? So one of the, I think, questions that was left as a question in the video, and I think it's shown up as an assignment problem, is from the approximation week, is again based on greedy. So I think for vertex cover, we ask you if, it makes sense to always pick the high degree vertices. So what are we trying to do in vertex cover? We are trying to basically cover all the edges in a graph. So it does feel like you should try to target vertices that have high degree because they cover the largest number of edges. And again, for most natural examples that you can think of, this strategy either gives you an optimal vertex cover or maybe at least a near optimal vertex cover, maybe. So it's really, I mean, you really have to think somewhat adversarially to come up with bad examples, and I mean, it's really hard because sometimes, I mean, for vertex cover, we know that greedy can fail quite dramatically, but for some other examples, it fails by a smaller margin. So in fact, for some problems, you can actually argue that the greedy strategies are not too far from the optimum, even if they're not exactly optimal. So the point is that when you're working on a new problem and nobody has told you what the outcome is going to be, your guess is as good as mine, right? So you have to really spend time thinking about the problem, playing around with examples, and sort of building your own intuition about it. And this is going to sound a little funny, but when I'm trying to come up with counter examples, there's a certain psychological barrier which comes from being attached to the algorithm that I've come up with, and I don't want to see it failing. So it's hard for me to think adversarially. So sometimes I literally imagine that this is an algorithm that a friend has come up with, and for some reason I want to prove them wrong, and then it becomes a little easier to start thinking about counter examples, right? So it's a really weird psychological trick, but sometimes you really want to put yourself in the shoes of somebody who is trying to break the algorithm to design like crazy scenarios where the algorithm will not work. And if you really fail after all that, then what you would have done in the meantime is you have built up you I mean you if you think about why aren't you able to come up with a counterexample, because in this situation the algorithm manages to save itself by doing this, in that situation the algorithm is fine because it does this other thing. So all of those little ideas or pieces of intuition can hopefully come together in some sort of a proof that the algorithm is actually doing okay. So thinking about counterexamples is sort of a really useful muscle to build. So it's good to get some practice sort of trying to either look at counterexamples that other people have built. So in the case of vertex cover, I think in the assignment there's actually a hint about what a bad example for greedy looks like, and I think you have to mostly reason about it. I think it's in the practice assignment. It's probably not in the graded assignment, if I remember correctly. So do sort of play around with those kinds of examples to get a feel for sort of what's going on. Like I said, at some point you'll go beyond the textbook algorithms and problems, and you'll kind of be solving problems that people haven't solved before. At that point, really, there's no answer key to check against. So you'll have to really, try both ways. You have to try and prove that your algorithm comes close to optimal. Then on some other days you will be trying to prove that, okay, there are these scenarios that could be really bad for the algorithm. So it's sort of a back and forth that happens very often when you're kind of working with approximation. So yeah, I think because we had a greedy strategy in approximation, I kind of jumped a little bit back and forth. So let me come back and talk about matroids again here. In terms of recap, it's basically okay, from a very practical point of view, the main thing you really need to remember is the definition, and have a good understanding of the definition, like what is the exchange property. That's really the main um, the main non-trivial idea there. I think heredity is sort of a relatively easier property to kind of remember and understand. The exchange axiom is one of the key things that makes matroids special in many ways. So just basically remember the definition well and know how to apply the definition. So for the limited purposes of the level at which we are looking at it, that's kind of that's a good place to start, and that's mainly what you're going to need to be able to tackle the problems in the quiz. We are not going to be asking about funky matroid based algorithms or proofs or any of that. This is mostly about being able to recognize a matroid when you see one. So just be comfortable with the definition, be comfortable applying it. Okay. In dynamic programming, the main thing is to really be able to think of when and how can you break up your problem into appropriate subproblems. So really the main theme here is coming up with recursive solutions. And once you can see the recursive structure, then there is a question of, how do we implement it? How expensive is it to implement, and all of that. And again, if you have a good sense of, if you have clarity on what your recursive substructures look like, you will be able to come up with a good analysis of how long your dynamic programming algorithm will take, what is the complexity. But remember that in DP, you're really exploiting overlapping subproblems so that you don't have to do the same work again and again. So let me sort of just contrast this, because when we say overlapping subproblems, when it happens, it's easy to see that it happens. But when it doesn't happen, then, well, I don't know. I want to alert you to scenarios where it doesn't happen. Okay. So for example, the classic DP example would be something like Fibonacci. So to compute the nth Fibonacci number, you make calls to computing the n minus 1 and n minus 2th Fibonacci numbers. For n minus 1, you make calls to n minus 2 and n minus 3. For n minus 2, you make calls to n minus 3 and n minus 4, and so on. So you see that this recurrence tree here, fn minus 2, is kind of totally redundant, given that we have already computed fn minus 2 right here. Okay, so when you do DP, basically you will not explore this computation path if you have already explored this one. So that's what we call memoization. You say check if the value has been computed. If it has, then there's no need to compute it again. So then you can use the fact that every value is computed at most once to basically observe that in this case, for instance, you're just going to have a linear time DP. And again, depending on what's comfortable, you can think of it in terms of writing down a recurrence and memoizing it, or you can also think of it as, populating an appropriate DP table where you're sort of populating it in a particular order, keeping in mind all the dependencies and everything. So that's sometimes called the bottom-up approach, because you start with the base cases and you work your way up manually, knowing exactly, at the your for loops will basically tell you what's the order of computation. So you're kind of working it out manually. In contrast, in the top-down approach, you just write your recurrence as usual, So it's kind of just the normal recursive formulation, but you have to be careful about remembering to memorize so that you're not making these extraneous redundant recursive calls. If you forget to memorize when you do recursion, then this whole thing can blow up and basically become exponential time. Okay, so again, from a very quiz perspective, these are probably not nuances that will come into picture too much. What will be more important is being able to understand the recursive nature of the solution. So often we'll present a problem, like I think in the review assignment, you may have this bookshop problem as an example. So you present a problem and you present different possible ways of doing it, and you just have to sit down and figure out, which one of these recurrences actually makes sense, which one of it captures the um, essence of what the problem is asking for, which one of these is correct. That's what you need to kind of get into. Occasionally, we may have a question that asks you to analyze the time complexity, but that's just a matter of being able to visualize the DP table and see, what's going on there. So that's the sort of emphasis that we have for DP. And I'll give you an example of a problem where you don't have this kind of repeating substructure, and that's actually a bit of a teaser for a future topic. But you remember the vertex cover problem, right? In vertex cover, you're trying to find a subset of the vertex set such that for every edge UV, uh, S contains at least one of the endpoints of that edge. So if you're trying to find the vertex cover for a graph G of size at most k, one thing that you can do is you can recursively try to find um, a vertex cover of size k minus 1 for these two graphs, where what are these two graphs? Basically, what I've done is I've picked an edge, UV. You can pick your favorite edge in the graph. It can really be anything. So pick your favorite edge, and you say that, well, if G had a vertex cover of size k, then it must have picked at least one of U or V just by definition. So suppose it picked U, right? So then it's picked U. So let's look at the graph G minus U. G minus U must have a vertex cover of size k minus 1 because the vertex U is already occupying 1 unit of space in the vertex cover. So the rest of the graph must have a vertex cover of size k minus 1. So that's this function call here, right? You try to find out if G minus U has a vertex cover of size k minus 1. Or for all you know, maybe there is a vertex cover of size k, but it picks the vertex B and not the vertex U. In that case, the graph G minus V must have a vertex cover of size k minus 1. So that is this function call. So I'm just saying this is I don't really, I don't really expect that all the details will be clear immediately, but maybe just believe me when I say that you can actually recursively solve vertex cover like this by trying out these two possibilities. And if the vertex cover finding algorithm reports yes on any one of these instances, then you can also say yes. Otherwise, you say no. That's the sense of the recursion. But notice that here there is basically, okay, so maybe it's not immediate right now, but you can draw out the recursion tree for a small example, and you'll see that there are really no overlapping subproblems. You cannot leverage or memorize anything. So this is a recurrence pattern that is exponential time, and there is no avoiding this exponential blow up. Okay, it's truly exponential time. You cannot do anything about it, in the sense that this recursion itself is not going to get fixed by hacks like memorization, because there's really, I mean, you could memorize, but you'll never really see a benefit to memorizing in any serious sort of way. All the graphs that are being generated are going to be different. So this is just so that you don't take for granted that whenever you see like a big recursion tree which is exponentially large, you don't automatically jump to the conclusion कि हाँ यहाँ तो savings हो जाएगा if we just memorize. It's not automatic. You really have to carefully check that there are overlapping subproblems. Are there overlapping subproblems? And if there are, then how much time can we save? So it really varies a lot from problem to problem. So don't worry if you don't understand the details of the vertex cover example, because I was deliberately sketchy about it. It's coming up in week 9, and you'll see like a full 20 minutes explanation of what is happening here and how we can improve the running time. But they will be slightly different ideas. You'll kind of will see a different set of hacks for trying to improve the running time of algorithms like these. So this is just a bit of a teaser for the kinds of things that are coming up later. But the reason I brought it up was mostly to alert you to the fact that don't take memorization for granted, right? So every algorithm really needs to be analyzed carefully on its own right. And then, well, we talked about flows. We talked about the duality between max cut and min flow. Sorry, the other way. What am I saying? So we saw the duality between max flow and min cut, and and here we saw a lot of applications as well. We saw how you could take problems that look nothing like flow and you can reduce them to flow. And I think in quiz 1 we had a terribly lengthy question that tested one of these applications. So hopefully, if I remember correctly, quiz 2 will not have any questions that are as wordy. And even if there are applications, they're going to be relatively easy to kind of parse and read through. But again, just I would say just recap, the flow algorithm. What are properties of max flow? The definitions, like the fact that it satisfies a conservation constraint, the fact that basically, yeah, just the whole setting of it, and how the algorithm works. Why doesn't the greedy augmentation work, and why do we need to be a little more careful? And what do we get at the end in the residual graph actually corresponds to a min cut. So all of these kind of little ideas are useful to remember, right? And also the fact that you can decompose a max flow into disjoint paths. That's also a useful fact that we have used in many applications. But yeah, if you had to focus on a small number of things, I would say basically just go back and make sure that you're comfortable with the definition of what constitutes a flow, and yeah, just the basic properties of flow. I think that should be enough. In terms of reductions, yeah, I mean, and I'm coming to reductions also in NP completeness. Basically, this is just the merrier approach to preparing. So the more examples you see of reductions, the more you're going to get comfortable with the idea of doing these transformations between often two seemingly unrelated problems, right? So that's something that basically comes from practice. So it talked about flows, and with NP completeness, I think it's really a matter of understanding the directionality of the reductions, so you can reduce a known hard problem to your problem. And if you do this in polynomial time, this implies that x is hard. Or if you have your problem and you reduce it to a known easy problem and you do this also in polynomial time, then this implies that x is easy. And these are really the two main things that you need to remember about reductions, right? I don't often say this, but if you want, you can commit this to memory, just so that if you are like confused on the spot, then you can quickly recall this. But hopefully, the logic is also clear. The logic is simply that you can chain an algorithm with a reduction to get a larger algorithm for the other problem. So, what do I mean by this? So suppose, for instance, we have a reduction from SAT to independent set, and somebody gives us an algorithm for solving independent set. Then we have an algorithm for solving SAT, and the SAT algorithm will say, so let's say that the reduction is F and the algorithm here is A. So the algorithm for SAT takes an instance of SAT as input, let's say it's some formula phi. And what it's going to do is it's going to run the reduction on phi, okay? And then it's going to say, okay, so this object here is an instance of independent set, because that's what the reduction gives me. The reduction takes an instance of SAT and turns it into a graph. It turns it into an instance of independent set. But because this is an instance of independent set, I can now feed it into the algorithm that I supposedly have for independent set. And this algorithm will tell me, was this instance an instance of yes instance of independent set or not. So whatever this algorithm tells me, I just return it, and that's going to be my algorithm for SAT. Okay, and this is true for really, any two problems. So if you have a reduction from, problem P to problem Q, then if you have an algorithm that solves problem Q, then with this combination, you also have an algorithm that solves problem P. So how do you exploit this chaining? How do you exploit this idea? You could say, well, I know how to solve Q. That happens, for example, in MaxFlow. I know how to solve MaxFlow. So let me use the MaxFlow algorithm to solve my problem P. So then you want to reduce P to MaxFlow so that you can leverage an algorithm. If you believe you're stuck with a hard problem, then you should try to go the other way. So you start with a hard problem and you reduce it to yours. And now if somebody says that I have an algorithm for your problem, then you can again use this chaining argument to say that, look, if you can solve my problem, then I can solve SAT, or I can solve, one of these very famous hard problems. Therefore, it's really unlikely that you have solved my problem. So that's kind of the logic when you try to show hardness with these reductions. Okay, so this is the directionality is really crucial. Remember to not sort of get confused and sort of do it in the opposite direction, because then that's not very useful. And most questions that we have in the assessments basically test your understanding of the directionality of the reductions, and also for you to be able to actually verify whether a reduction preserves equivalence or not. Notice that equivalence is really key, because for us to be able to say that when you return the output of this algorithm, you have correctly solved this problem, that only happens because we know that we have mapped yes instances to yes instances and no instances to no instances. So if this algorithm does its job properly, then we have correctly solved the source problem. But if you don't have equivalence, then all bets are off, right? Then you really cannot say anything about anything. Okay. So, all right. So that's what I wanted to say in the context of reductions. And I think I already spoke a bit about approximation here. Again, just remember this one. Essentially, at this point, there's only one key definition that you need to remember, and the main approximation algorithmic technique that we have seen is this LP rounding. So just be comfortable with the LP terminology, and I think you're good to go in terms of the fact that if you have like the difference between LP and ILP. So one of the key ideas here is that ILP is hard, but LP is easy algorithmically. But ILP is meaningful, and LPs are, basically things that can give you garbage output. The optimal solution to a LP is going to be a bunch of these sort of real numbers. They don't mean anything for most problems. So how do you transform a LP solution to an ILP solution without losing too much in terms of the quality of the solution? That's the main game. And often it gets complicated, but we have seen the example of vertex cover, which I think is quite cute and I think easy to understand, I hope. And basically, I think there's an assignment question that asks you about the threshold. I think just make sure that you understand how that works, and I think that's the kind of recap that I think is relevant for the quiz. Okay, so with all that said, let me come back to Arya's question, which is about why is it well, hopefully it's clear why it's important that this reduction should run in polynomial time, because that's what tells us that this composed algorithm here, which combines the reduction with the algorithm, that whole thing runs in polynomial time only when the individual components f and a themselves run in polynomial time. If there's a blow up in any of these places, then you have a problem. So, so you were asking for examples of reductions that don't run in polynomial time. So, I mean, To give you an example that you may have already seen, but I'll just try to draw your attention to it because you mentioned pseudo polynomial running times. This should feel familiar. So let's look at shortest paths on weighted graphs. So you're trying to find shortest paths, right? So let's say you have a start vertex S and you want to find the shortest path to some vertex V, but now your edges have weights on them. Let's say the weights are just like natural numbers for simplicity. And we know that we cannot do BFS, right? Because what's wrong with BFS? Well, so for instance, you might have a situation where, let's say, these two edges have weights 50 and 70, and this edge has weight 1 or something. And let's say this is your start vertex and this is U and this is V. So you can hopefully see that the shortest path is SUV. The shortest path actually has two edges, right? And it has a total cost of 51. But on the other hand, what will BFS do? BFS will say, okay, SUSV, because it'll put S at the head of the queue, and then it'll queue up U and V, and it'll put both U and V on the top layer. And it's just going to say that, okay, these single edge paths are the cheapest. So it's actually going to give you a one edge path from S to V, but that has cost 70, right? So that's not the shortest path. And to be honest, you can't really blame BFS for this, right? Because nobody told BFS about the costs. So BFS cannot take cognizance of the costs because it doesn't know about them. It's treating this like an undirected graph. By the way, I'm assuming that although we have not officially covered BFS in this course, BFS is fine, right? Does anybody want me to recap how BFS works? This is breadth first search. You just give me a quick +1 in the chat to confirm that BFS is okay. Or if you want me to recap it, just let me know that you want to recap it. Okay, awesome. So BFS is fine. So hopefully it's clear that BFS can go wrong on weighted graphs. And one way to make BFS work for these weighted graphs is to actually take a weighted graph and try to reduce it to an unweighted graph or transform it into an unweighted graph on which BFS can do the right thing. So if I have this example that I just showed you, so this is a weight of 50, this is even longer with a weight of 70, and then this is a weight of 1. So one way that you can transform this weighted graph, so this is the reduction that we're trying to perform. I want to go from a weighted graph to an unweighted graph. And the way I'm going to do that is by subdividing. So let me just make this a bit easier by making this 5 and 7 so that I don't have to draw too many points here. So going to say, well, now in this unweighted graph, the cost of getting to U is 1, 2, 3, 4, 5. Okay. So U is going to end up on the 5th layer of the BFS tree because we have artificially increased the cost of getting to U by subdividing the edge between S and U with these 4 dummy vertices. These are dummy degree 2 vertices that basically prolong the length of the path between S and U in proportion to the original weight. Okay, so notice that that's why I sent natural weights so that this reduction is easy to do. If your weights are like real numbers or something crazy, then at least this idea will not directly work. But notice that at least here this is sort of fine. And now if you do your if you do your BFS, it'll give you the correct path. So in fact, even with these new numbers 5, 1 and 7, the path via U to V is shorter because it's basically 6 units long, as opposed to the single edge path in the weighted graph, which would have cost you 7. So this is indeed the better path, and indeed now BFS will find it because now in this graph you have taken cognizance of the weights, right? So this is a In some sense, a valid reduction, you started with an instance of shortest path on weighted graphs, you reduced it to an equivalent instance of shortest path on unweighted graphs, where you know that BFS will do the trick. And so this is a positive reduction where you're saying, okay, let's assume that we don't know Dijkstra. Okay, so Dijkstra is what comes next, because as we are going to argue, this reduction is actually not a very good reduction. It's too expensive, and that motivates why people actually do Dijkstra. Okay, but for a moment, just bear with me. I want to give you an example of how. So here we are reducing x to y. X is shortest path on weighted graphs, y is shortest path on unweighted graphs. And this is a problem we know how to solve. We know how to solve this using BFS. This is a problem we are trying to solve. So we just came up with this cute reduction. It preserves equivalence in the sense that, if the question is there a path of a certain length between, let's say, S and V? If the answer is yes in the weighted setting, then the answer is yes in the unweighted setting after you transform it like this. And the no instance is also mapped to no instance. So this is a perfect reduction from an equivalence perspective. But if you think about the running time of this reduction, right, I claim that it's actually an exponential time reduction. And that may or may not come as a surprise. I'm not sure. It looks like we're doing some chindi stuff here. We are just adding some, stupid degree 2 vertices. How much time can it take, right? But the issue is, what are we measuring the time in terms of? You're measuring the time in terms of the size of the input. And the question is, what is the size of the input? Well, if you have a normal graph without weights, the size of the input is, basically, okay, so Manisha is suggesting that it's n squared. That's a good guess, but the problem is that we have not taken into account the magnitude of the weights that come on the edges, right? So just as an example, in this reduction, let's say your graph has an edge between u and v, right? Whose, where the weight is, the weight of the edge is, let's say, 2 to the 516, right? So this is somehow a very heavy edge for some reason. We have, we have a edge that has a large weight. Now, to store this number in memory, right? So normally, you may have your favorite representation of a graph. Let me just say that we have stored the graph as an adjacency matrix. And so Manisha, I'm not sure, maybe you were answering my question about the size of the input, and in that case your answer is absolutely right. Depending on whether you choose an adjacency matrix or list, it could be slightly different. But for an unweighted graph, the adjacency matrix basically takes n squared units of space. Every entry is a 0 or a 1, so you're really needing only n squared bits to store the entire structure of the graph. But if it's a weighted graph, then let's say the entry between the uth row and the vth column, that entry is not just a 1 to say that there is an edge from u to v. That entry is actually going to be this number, because the number tells you what's the weight of that edge. And now basically you are taking, how much space are you taking? You're taking log of the largest weight times n squared. That's the total amount of space that you need. That's an upper bound, right? So in this case, let's say all the weights are 2 raised to 516 or at most that, then you need maximum 516 times n squared bits to store all the information about your weighted graph, right? So my size of input is 516 times n squared, right? But when I'm constructing this transformed graph, right, I have to make some 2 to the 516 subdivisions, right? That is way too many. It's exponentially large in the amount of space that I have needed to store my input. Okay, because in the worst case, you may have to do this 2 raised to 516 for all your edges, right? So so you needed only 516 into n squared bits to store your graph. That's the size of your input. But by the time you've run your transformation, you have spent 2 raised to 516 times n squared sort of units of time, which is really not polynomially bounded in the space that you have. In fact, imagine that your graph is just this, right? There is, it's really just, these two vertices here, and this number. So the size of your input is effectively log of w, that one weight that you have to store, but the amount of time you spent is like w. And this is misleading because w feels like, oh, it's just w, you're spending w units of time, w is linear, but it's really hiding an exponential function. W is 2 raised to log w, and log w is your size of input. So that is why this would be called a pseudo polynomial time reduction, because it's polynomial if all the weights were small. So let's say all the weights were like within n squared and cubed, something like that, then you would be in business, because even if you need log n squared bits to write down a weight which is n squared, you have anyways taken up n squared units of memory to represent your graph itself. So it's okay. Your input size is n squared. If you need n squared time to do the subdivisions, it's still fine. So if your weights are small, then your reduction will run in polynomial time. But if the weights are unbounded, then your reduction is technically taking exponential time. So that's the pseudo polynomial thing. In the lectures, I may have had a different example using, or I may have mentioned pseudo polynomial in the context of set cover. That's subset sum, not set cover, but subset sum. And basically, the idea is whenever you have numbers, please watch out and be careful. So things like primality testing, factorization, subset sum, knapsack, edge weighted graphs, vertex weighted graphs, whatever. Whenever you see numbers, just be a little bit alert about what is going on. So this hopefully is a satisfactory example for Arya for as a reduction which preserves equivalence, but in many situations it's not a polynomial time reduction. Yeah.
Yeah, yes, ma'am. But okay, so I understood this example, but can you help me understand what is the role of the constraint? So if we look at this review to question number 3, which we talked about in the beginning,
Yes.
so over there, a certain set of constraints are given. Now, when we talk about a reduction, we basically talk about the process of changing one problem to the other, right?
Yes.
Constraints the constraints are basically applied on the solution that we present, right? So, uh,
Okay.
how do we take into account the
Right.
constraints and the complexity of the constraints themselves? Like, what does that even translate to?
Okay, correct. So I think let me just quickly review this. So I do realize that I think, yeah, sorry, I think I've probably spoken quite a bit, as a result of which it's on the hour. So if anybody has a time constraint and you have to leave, please feel free. If you have, Prashant, you've raised your hand. Do you want to ask a question?
Yes, ma'am.
Yes,
But
please
my
go ahead.
question is regarding the two approximation, three approximation thing. So,
Okay.
so I'm not sure whether it's the right time because you are in middle of.
No, no, that's fine. I think we'll sort of queue it
Okay.
up. Why
So,
don't you ask your question and then we'll see in which
okay.
order to address it.
So, ma'am, when we went through the derivation for the LP reductions
Yes.
of the problems, then we actually applied the constraint that okay, or you can say the assumption that okay, greater than or equal to zero point 0.5 will be converted into 1. So we came up with the two approximation.
Right.
Then there comes a question that okay, what if we do it for 1 by 3? So we came up with the answer as a 3 approximation, right? What I was thinking that okay, probably we can reduce this thing. Okay, probably 1 upon very big number, so that it will become like a very small. So it should not go to the infinity. There must be some other thing that actually cap it, because if I do it something like that 1 upon n, where n is very large, it means the threshold is decreased to the minimum,
Right.
approximately equal to
Right.
0.
In the
So
limit. Yeah.
there must be a limit.
Correct. Yeah, so that's a very valid question, and I think you're anticipating what happens in some of the more sort of subtle approximation algorithms, or I would say there are other regimes of approximation. So yeah, so Arya is saying that you would probably never threshold it below n. Would not make sense. Also, notice that lower thresholds are. I mean, hopefully, it's clear that because this is a minimization problem, a 3 approximation is worse than a 2 approximation, right? So if somebody guarantees you that I will give you a solution that is within a factor 2 of optimal, so let's say the smallest vertex cover for some graph G, I can draw you an example, but in the interest of time, let's just do an abstract example. So let's say that the vertex cover of G is 20, and somebody says I have a 2 approximation. That means that what they're promising is that the output of their algorithm is at most 40. But if somebody says that they have a 3 approximation, then their commitment is that the output of their algorithm is at most 60. Right now, if you are interested in a smallest vertex cover, then hopefully it's clear that you would prefer this algorithm over this one, right? So you would really not be interested in higher orders of approximation if these smaller approximations are available. Of course, it changes a bit if you're trying to approximate like something that you're trying to maximize, then it would basically go the other way. So if somebody guarantees you, let's say, 1/100th of a quantity, right? So the idea is that, okay, so let's say, so independent set is normally something that you want to maximize. So let's say that an independent set, some graph G has an independent set of size 50. If somebody guarantees a half approximation, that means that they're promising you that they can return an independent set of size at least 25, right? Whereas if somebody guarantees you a 1/5 approximation, then they're promising you that they can definitely get you at least 10 vertices, but beyond that, there are no promises, right? So here, you would prefer the zero 0.5 approximation over the 0.2 approximation. So here, in some sense, the larger number is the better one, whereas for minimization problems, you would be interested in coming as close to the optimum as possible, so the smaller factors work out better, right? So now, sometimes what you can hope for, so these are all like the factor of approximation, and all of these things that I just said is basically constant. And just like we have NP completeness, there's also like a hardness theory within approximation also, where you say, well, you cannot do better than, let's say, you don't expect to do like a 1.5 approximation for vertex cover in polynomial time, right? You can make statements of that flavor where you say that, okay, you can come close, but only this close. Beyond this, if you can manage more better than this in polynomial time, then again something somewhere collapses in terms of some conjecture being violated or whatever. But this idea that you were talking about, where the approximation ratio is no longer a constant, but it's potentially a function of n, and how does that go? And do you approach something in the limit? So these are ideas that are very much present in approximation algorithms. So these are called approximation schemes. So you can basically demand from your approximation algorithm that you come epsilon close to the optimal, right? So your epsilon could be, so let's say, it's let's say for a maximization problem, you want to be within an epsilon factor, which is where you want epsilon to be as close as possible to 1, right? So we saw half, we saw 1/5, we saw half was better than 1/5. If somebody gives you 3/4, that's even better, and so on. But instead of these specific constants, you want a general parameter saying that, okay, I want to come epsilon close to the input. What is the price I have to pay to come this close to the input? And typically you'll have some running time, which is some function of 1 over epsilon. So if you say that I want to come half close, then let's say you have to pay a price which is in terms of let's say the running time is n to the 1 over epsilon. So if you want to come within a factor of half, then 1 over epsilon would be basically 2, so the running time would be n squared. If you want to come if you want to come let's say in this case, okay, so basically what I want to say here is, I don't know if I have the ratios presented here correctly for maximization. I think this is, well, the point is that the running time becomes higher, or it becomes worse, the more you demand from your approximation ratio, right? So if you want to come closer to opt, you basically have to pay a higher price in the running time. And that's that's kind of how a scheme works. It's basically a one algorithm, but the running time of the algorithm is parameterized by epsilon, and now you can pick as somebody who is running the algorithm, you set the value of epsilon right in the beginning, and you can see how much running time can you afford, and you can say that, okay, I can afford this much running time, so I want to come this close to the solution. So that's so basically it's one algorithm which contains many algorithms in it. Like basically it's a full spectrum, and indeed you can kind of push it to the limit, but it'll kind of not make sense to go too far, because if you just try the closer you try to come, like if you just say that, oh, can I just say epsilon equals 1, can I hit the optimum, then typically the running time will be something that will be sort of way off the charts, or it would not make sense. So well, I mean, that depends on specific examples, of course, but this idea that you have of reaching some sort of a limit, that is realized with what you would call an approximation scheme, basically. Yeah. So hopefully the idea makes sense. I think we have to say it a little bit differently depending on whether it's maximization, but but what these things are called, basically, if you want to look it up, this is, you're looking for what's called a PTAS. This is a polynomial time approximation scheme, and I hope that at least in spirit sort of answered your question.
Yes, sir. So just one thing that clarified is that we are actually talking in terms of the scheme, that whether it's a 2x scheme or 3x scheme.
Right.
Now, one related question is that the maximum, because we are constrained that it should be greater than equal to 1. So, I think it is equal to 1. X1 plus x2 equal to 1.
Right. So
So,
in fact, I think, let me just say that I think let me write this out explicitly. For maximization problems, we want to say that we are within 1 minus epsilon of opt. And for minimization problems, so we want to say that we are at least 1 minus epsilon. And for minimization, I think I will say we are at most. And you're looking at epsilon being strictly greater than 0. So for instance, for a minimization problem, let's say epsilon is 1, then that is a 2 approximation. If epsilon is half, then you're saying that it's basically a 1.5 approximation. If epsilon is 1/4, it's a 1.25 approximation, and so on. And for a maximization problem, if epsilon is, say, half, right, then you're looking at a half approximation, like we said earlier, for within a factor of half. If epsilon is 1/4, so epsilon is, as epsilon becomes smaller, you come closer and closer to optimum. So if epsilon is 1/4, then you're basically within 3/4 of the optimum. If epsilon is 1/10, then you are within 90% of the optimum. Does that make sense?
yes, ma'am.
Okay.
Now, there's one, you can say, half cooked thing that is bothering me is that uh, when we are comparing the means, when we are assigning 1 to an edge, then we are doing x1 plus x2 means for the two vertices. Now, if I have n edges, it means I have 2n vertices, for that matter, from the perspective of the equation. Then it will, at the minimum, it is going to select half of it, because there is a constraint that is, the sum must be equal to 1. So I was just thinking that it might be that it will never go beyond 2, because at max you have to select half of it, or
Mhm.
less than half of it.
Right. So at least one of these values will be at least half.
Yeah.
And I think if your point is that by changing the thresholds we cannot get a factor better than half, because in the worst
Yes.
case, yeah,
I'm just trying to point
yeah,
that, but it is not
yes,
very concrete in my mind. But it's just
no,
like that
no,
I'm getting
yeah.
that point.
No, I think you're right. So, for example, if you look at a complete graph, for instance, the LP opt is going to basically say one half to everything, right? And you know that the vertex cover, so if you have by a complete graph, I mean all edges are present. So it'll be something like this. So if you want, you can keep going. So the optimum vertex cover for a complete graph on n vertices is going to have size n minus 1, because you have to pick all but one vertices. If you leave out any two vertices, then that edge will be uncovered. But the LP has the luxury of saying that, oh, I will assign a value of half to all the vertices. So the LP value is going to be n by 2. So this basically this shows that the LP opt can be like, it really can be as bad as half. And in fact, what you are talking about, I think that intuition is absolutely right, that you cannot push this idea beyond, like, this factor of 2 is the best that we can hope for. And this idea is formalized in this notion of what is called an integrality gap. So the integrality gap of this LP is basically saying that, okay, I mean, your um, LP and ILP opts can have can be off by a factor of this much. In this case, that factor is indeed 2, exactly as you're pointing out. And if you want to look this up a little more, then the keyword to look out for would be the integrality gap. But you're right. But there could still be the question of, is there some completely different algorithm that can bring us a approximation for vertex cover that's better than 2? And there is a more sophisticated answer to that, using a lot of complexity theoretic machinery, to say that, well, even that we do not expect. If that happens, then there's going to be some other conjecture which gets violated. So but that is an independent statement. I think what you are observing here is that at least from the LP we cannot squeeze out anything more, and that's a valid observation.
Just to add, Miss, this is not a question, but because when I was going through this question in my mind, I tried to search something. I got hand with some research paper or some kind of a notes of some professor. I think some MIT professor, and there was a
Okay.
question. Actually, there was a question which was something related to saying that it cannot go beyond 1.78. Although it was not answering my question, but it was saying that it cannot go beyond 1.7 something. So I'm not sure whether this is right or wrong, because it was a question only.
Okay. Yeah, I think the 1.78. Trying to see if. Yeah, I'm trying to see where that might be coming from. If you have a pointer to either the notes or the questions that you've seen, then maybe I can make
Sure,
a more
ma'am.
informed sort of a response to this. Off
Sure.
the top of my head, yeah, I mean, not 100% sure where that might be coming from. So, yeah, just drop me a pointer, and I will
And the
try to
scheme
figure
that
it
was
out.
mentioned was also not very straightforward. It was very complex kind of jargon, kind of a sentence. It was in the scheme.
Okay. So I think, I mean, yeah, I mean, that is a. Yeah, I mean, that is a claim that I have seen for in some other contexts. I'm not completely sure that I've seen it for vertex cover. And I think it comes up as an integrality gap as well. So, yeah, I mean, yeah, I mean, in fact, 1.78, I think, is a well known constant in a slightly different. In a slightly different situation. So yeah, if you drop me a pointer, I think I can try to
Okay,
elaborate on it, maybe next time. Yeah.
okay, ma'am. Thank you, ma'am.
Okay. All right. Thanks so much. Okay, so I think if we have, assuming we have addressed Prashant's queries, maybe I can circle back to what Arya was asking, but by now I think I have perhaps forgotten a little bit. Arya, can you remind me where we were?
Yeah. So I was asking that how do we take into consideration the complexity of the constraints? Because
Right. Okay, so we
yeah.
wanted to quickly go over this. So, okay, I think I should probably apologize for that terminology. By constraints in that question, I really just mean that these are clauses that we are adding to the formula. So some people, refer to the clauses of the formula as constraints, because that's really what the formula is doing, right? It's saying that, okay, you have to satisfy this clause and you have to satisfy that clause. So each of these clauses are really like the implicitly imposing constraints on the variable. So for instance, if I have a clause which says X or Y, and I know I have to satisfy this clause, this is really a constraint saying that you have to set either x to true or y to true. You cannot get away with setting both of them to false, right? So that's all that is happening. But yeah, I think let me just spend a couple of minutes recapping what this reduction is. So we have like basically we have a graph which has n vertices, and what we are going to do is we are going to introduce bn variables. So this is like, let's say we are going to have xij. So I ranges from 1 to b, and j ranges from 1 to n. And the idea is that xij, if xij is 1, then uj is the ith vertex of some independent set. So we are trying to capture some independent set, okay? And so we are saying, suppose we line up the vertices of an independent set. So suppose u1, u3, u5 form an independent set of size 3, then we are going to basically say something like x11 is true, and then x23 is true, and then x35 is true. That is how we want to set up our formula. So our formula will be so coming in the other direction, if I look at which of my variables were set to true, so x1 something was set to true, x2 something was set to true, x3 something was set to true, I just go and read off these labels, okay? And basically I'm going to say, okay, u3, u4, u5, these guys form an independent set. That's how I want my formula to be set up. So notice that for this I basically need that, among all the xi somethings, x, so x11, x12, x13 up to x1b, right? I want one of those variables to be set to true, right? And that will give me basically the sense of, what is it that I chose for my independent set, right? So that's kind of what I want. So that is my first constraint. I want to say that so by first constraint or clause, whatever that is, so I want to say that x11, x12 and so on up to x1n, at least one of these fellows must be set to true, because that is going to give me a signal for what is the first vertex that I'm choosing in my independent set. So I'll just have a clause which says one of these must be set to true. Similarly, x21, x22 and so on up to x2n, I want one of these also to be set to true. That will give me a sense of what is the second vertex in my independent set, and so on. So I'll have b such clauses or b such constraints, however you want to think about it in terms of terminology, right? So that is one group of constraints. What that ensures is that when I look at my, the set of variables that were set to true, I have a set of labels, right? Which tell me what are the b vertices that I should be picking in my independent set. But there is a danger that all of these labels, for example, may end up being the same. So I don't really get b distinct vertices in my independent set. Okay. So I want to prevent that. I really want all the b vertices to be the same. So I want all the b vertices to be different, not the same. I want all of them to be different. So we'll add a constraint saying that basically if you have, um, xij, and then you have xkj, right? So if I and k are different, then these fellows should not simultaneously be set to true. So I think in the question this was I prime, so let me write I prime. So for any I prime pair, I don't want these fellows to be set to true simultaneously, because then I don't really get distinct vertices for my independent set, right? So for example, I'll have a constraint which says xi3 bar and x53 bar, okay? That's one example. So I want to say that, okay, both the first and the fifth vertex of my independent set should not be u3. They have to be different. But like this, I will have basically b squared or b choose two constraints. Basically saying that, okay, make sure that you pick distinct vertices. And similarly, there'll be a constraint which kind of says that you want to make sure that if you have a clean signal. So what should be the first vertex of my independent set? I want it to be exactly pointing to one vertex. So I don't want x13 to be true and then x14 to be true and then x17 to be true. Then I don't know, do I pick u7, do I pick u3, do I pick u4, which vertex do I pick, right? So it's confusing. So I'm going to say that, well, on the first coordinate I pick exactly one vertex. So this constraint already ensures that at least one vertex is being chosen. This constraint will ensure that you don't choose two vertices, you choose exactly one, because this constraint says something like x17 or x13 bar, for example. This will ensure that you don't set x17 and x13 both of them to true simultaneously. So that's all that this constraint is doing. And finally, you want to ensure that all the vertices that you picked actually are independent. That is the heart of the matter. So you have one final constraint which says that if, for example, x13 is set to true and x24 is set to true, then we should not have a problem. So if 3 and 4 have an edge between them, then we don't want these two variables to be set to true simultaneously. So for every pair of edges and for every pair of coordinates, you will have one clause which says, boss, don't do this thing, where you pick two endpoints of an edge in your independent set. So all in all, you have generated a whole collection of clauses. And the hope is that if you find an assignment that satisfies all of them, from that you can just read off an independent set. And the hope is that if you have an independent set, you can actually come up with an assignment as well. So is the structure of the reduction clear, or did I lose you somewhere?
No, no. This is I mean I got it from the question itself,
Okay.
but yeah.
So in terms of
So,
constraints, basically, yeah, I mean, just think of the constraints as the clauses. And in this case, well, I don't know if I want to give away more about the question by talking about, like, you have to think about, whether the number of constraints you generated, the sizes of the constraints involved, if all of that can be managed in polynomial time or not. So really count everything and see if it
uh,
adds up
yeah,
properly.
which I did just now, but I
Okay,
mean
good.
uh, I believe I got the answer, but point is that I just had some clarifications,
Okay,
like in general,
sure,
which
sure.
is that like when we talk about 3 sat for the for as a hard problem, right? So 3 sat, I'm just revising the definition, which is that you say that it should be in conjunctive normal form and it should have like at max 3 literals, right?
Right.
And let's say and then obviously from the thing that you said in the lectures, it is that 2 sat and below is like solvable in polynomial
Yes.
time, but 3
Yes.
sat and above is not solvable.
Yes.
Okay, and the other thing is that my other question was that so I don't know. It's a bit leaning to what the question in the assignment, I mean, the review assignment is, but just a very specific thing, which is that if we have, let's say, an OR operation over various these literals, so to say,
Mm-hmm.
and there could be n of these.
Mm-hmm.
But my query was that let's say I just have an OR operation over various literals, okay, and so then that is I would say I mean trivially supposed to be in conjunctive normal form, right? Because I can consider this entire thing as one clause, and then that makes it as one clause itself, right?
Yeah, yeah. This is one clause. Yes. This is one
Yeah.
clause. This is another one. And you're taking the
Yes.
and of all of these clauses. So the CNF format of this is not really in question. Yeah. It's,
Right. So no.
yeah,
So basically, trivially speaking, one clause itself is already in CNF format, right?
correct. Correct. This is not a three-sat formula because these clauses are long. But
Yeah.
if you want, you can convert it to three-sat. But I think the question deliberately does not claim to reduce to three-sat. We are just reducing to sat. But if you want, you can also convert a general SAT formula into a three SAT formula. That's also doable.
Okay. Uh, Yeah, okay. I mean, maybe using De Morgan's laws and things like those, right?
Well, it's a little more than De Morgan's laws. So you can use De Morgan's laws to go back and forth between CNF and DNF. That you can do. But again, there you have to be careful because De Morgan's may cause a sort of a blow up in the size of the formula. So you have to be a little bit careful when you use De Morgan in a very sort of a general setting. In specific cases, it may be fine to do. But yeah, if you basically have a longer formula, so let's say I have x y z w a or something, I can convert this to a three-sat formula by introducing some sort of dummy variables. Like, so I can introduce a dummy variable p here, and then I can do p bar here, and I can say this is z, and then another dummy variable q, and then this is q bar, and then a. So x, y, z, w, a. Sorry, I think I needed to do both. Yeah, so this is essentially like a pretty standard conversion, I think. From so essentially, what do you want? You want that this formula is satisfiable if and only if the formula below is satisfiable. And the point is that these newly introduced variables p, p bar, q, q bar, they can be set to like take care of some but not all of the newly found clauses. So basically, if you set no matter how you set p and q, you cannot satisfy all of these for free unless one of x, y, z, w, a is set to true, right? So if all of these guys are set to false, right, then it will not be possible. So here then you will be forced to set this to false. Here you will be forced to set p to true, and then you will basically lose out on this clause. So basically you cannot afford to not satisfy the original clause even in this three set formula. But once you've taken care of something, if at least one of the literals in this long clause is true, then you can use that as an anchor point, and then you can use these dummy literals to satisfy the rest of it. So this is not it's not difficult, but I think it will take a little bit of staring at it to convince yourself that this actually works. So I would say think of this as an extended hint to you know try it yourself basically.
Yeah, yeah, I got it. That's fine. But so my question was that so you have this X or X Y Z W A clause, right? Letters like basically they have or in between them, right?
Correct.
So
Yeah.
uh now basically this by
This
itself
would
is
be it.
trivially also in CNF, right? Because
Yeah. The
there's
top one
only
is CNF and the bottom is
yeah,
also CNF because these are
yeah.
ANDs.
Yes. So if I take the top one, basically, if I talk about satisfiability of this top one, so can I say that this falls in what, 5 sat or something?
Yeah, this particular one would be 5 sat, but you could have a formula which has a mixture of different things. Something would be 5, something would have 7, something would have 100. You can
Yes, yeah,
flatten out everything. That's the point. Yeah.
right. But now when we say that any sat above 2 is NP, this NP complete, right? So
Correct.
uh, then but in this case, like to satisfy this formula, I can just put any variable to be true and then it completely evaporates, right? So why
Correct.
is
Correct. That's because like this is one sort of easy instance. I mean, that way it's like, we say that vertex cover is NP complete, but if I give you a graph which is just an edge, you can see that, there's just a vertex cover that has one vertex. Or if I give you a complete graph, you can tell me that, oh, the vertex cover is like n minus one if the graph has n vertices. So a problem in general being NP complete does not mean that there will not be specific instances that are easy to handle, right? So there will be like on some inputs you might just find yourself in a situation where that input can be handled easily, but your algorithm doesn't know what inputs are coming its way, right? Is it going to be like a stupid input like this, or is it going to be some crazy complicated thing with like a million variables and a billion clauses interleaved in some very complex ways? So the algorithm that you design has to handle the entire spectrum of all possible instances. And NP completeness is basically to say that you cannot design an algorithm that will correctly work efficiently on all of those possible inputs. But there's nothing stopping an algorithm from saying that, oh, if you give me a formula where, let's say, all variables only occur positively, then I'll handle that in polynomial time. That does not contradict the NP completeness of SAT.
Okay, and what happens if, let's say, in a particular, again leaning to the question in the assignment, but in a particular reduction, I only get formulas of this kind. So by theory, I might say that, okay, some NSAT is NP complete for that matter. But in this case, my format of the NSAT is in a very simplistic format. So then can I say that the reduction goes in and completes it in time?
Well, yeah, so if your reduction, so it's a great question. If you manage to design a reduction that only generates certain simplistic kinds of formulas, then you can say that, well, SAT is NP complete even if the input was restricted only to these kinds of structures. So, for example, it's very unlikely that you'll have, for example, let's say a reduction from some NP complete problem like SAT itself in general or vertex cover independent set to an instance of SAT where all the variables are always positive. That will not happen because you know that there is an algorithm that can solve that in polynomial time. So then again, you would basically be implying that P equals NP. But if you can observe that, maybe there's something else that's special about the formula, then yes, then you're arguing what is called hardness in a restricted setting. You're saying that, okay, I know that not only can you not solve SAT in general, but you also cannot solve SAT uh, you know, um, uh, when the formulas have this particular structure, because my reduction is only generating formulas that have this structure. So this can be said of graph problems as well. So let's say in your reduction from, say, 3 set to independent set, you observe that you're only generating graphs where, I don't know, maybe the diameter is small or the maximum path length is small or the maximum degree is small, some property, right? So then you can say that, oh, independent set is hard even when the maximum degree is bounded, because my reduction is only generating such graphs. So I'm not saying our reduction actually generated only such graphs. We'll have to go back and check. But in principle, if you have a reduction that's only generating a certain style of instances, and you can prove that, then you have actually shown that your problem is hard even on a restricted class of input.
Okay. Okay, ma'am. Yeah, I think I got some ideas. Fine. Like maybe we can discuss this after the quiz as well. So
Yeah, sure. Sounds good.
yeah.
You're definitely asking all the right questions, so that's awesome. Yeah, I think we're now, I think, past and the 90-minute mark, I guess. So, like I said, I'm of course always happy to chat for as long as for as long as we need to. But I don't know if it's getting late for some of you. So let's see. Maybe I'll just go around once again and ask if there are more questions. Maybe especially ahead of the quiz, but even in general, we can take one more round of questions and then maybe try to see if we can wrap up our discussion. Okay.
I mean a trivial this thing.
Yeah.
Like even in the review assignment itself, the second review assignment, like this is a fourth question where we have to work out a LP, right?
Okay.
So
Yes. The
over
threshold.
there, there's a small, I mean, a symbol which is the opposite of the belongs to symbol, right? So
There was
what
about
does that mean?
Um. Okay. Is there?
I mean, an inverted epsilon, which is like a mirror
so
image of.
we generally say like we exist in U, for example. So that E is actually printed mirror image of it. So
Yeah, it's actually we could have written it straight also. It means exactly what Prashant is saying.
I didn't get what Prashant is saying, to be
Yeah,
honest.
yeah. E belongs to E, and then that belong symbol would have pointed in the right direction. I think I just wanted to keep the, like, for aesthetics, I think I wanted to keep the subscript E coming first all the time. So it's to be read as B belongs to E only.
Okay, ma'am. Okay, yeah.
Yeah.
Okay.
So it's just that yeah, now the set, like, yeah, the set is on the left and the element is on the right. So that's why the belonging is going the other way. No idea why the highlighter was on, but yeah, so we're just saying that V belongs to S. That's the spirit of it. Oh, sorry. I think for some reason my screen is out of sync. I was just trying to write out what I said, but hopefully it's clear. So what all that we mean is that the vertex V belongs to the edge. We are going over we're summing over all the edges that the vertex belongs to. That's all.
So, ma'am, on the same question, there is another notation where it is written like E equals to V. So can I read it in the same spirit that okay, we are trying to say that V is the participating vertex in the edge E?
V is the participating vertex in the edge E. Yes. Can you tell me in which
No, the
where
same question, same question,
same question?
but it is in the options actually.
Um, right. So
Can I share my screen?
yeah, sure. Feel free to
But,
share.
then my answers will be visible.
Yeah, I think Arya also mentioned this constraint. Yeah, so no, that's fine then. Basically, yeah, let me see if I can get whatever. Um,
Yeah, it is in the first option actually. So
okay,
A option.
so what does the first option say?
There is a sigma, and underneath it, it is written E is equal to V.
So does it say E is equal to V, or does it say E belongs to V? It should be E belongs to V. I mean, it's really the same thing in all the options. We are summing over all the edges that contain the vertex V for all V in the graph.
It
So
says E is
it
equal to
will.
V, so that
Ayo,
is
it
yeah.
shouldn't say E equals V. I'm sorry. Yeah, just treat it. Yeah, so I think Prashant, the answer to your question is yes.
Okay.
You should treat
Thank
it
you.
as a
Thank
sum
you.
over all the edges that contain the vertex V.
Okay.
So so yeah, can I just request the course team to make these two small announcements? One is that the letter B should be visible in the first two options for the independent set reduction, and I think this in this case is not E equals V, but E belongs to V. I think we can just post this as announcements. Yeah. Okay, so I think this is something that I'll make sure to follow up and get out
The deadline is today at 12
today at midnight.
midnight
Okay. All
anyways.
right.
Yeah.
Okay. All right. Let's see if yeah. So I think I wanted the recap assignment to have a deadline ahead of the quiz. In fact, perhaps this live session would have been a little more freely done if we had discussed tomorrow, but then I think you wouldn't have gotten these clarifications. So maybe it's good that we met today itself. But okay, all right. So we'll still try to get this across to you folks. And I don't know if it's too late to get a bit of an extension. I'll try to find out what can be done, but at least you folks hopefully have the correct version of the questions in mind. Okay, so sounds good. I think let's. So Arya, did you have anything else, especially that's time sensitive? I know we have more to discuss, which we can do after the quiz, like you said. But anything else?
No, ma'am, not right now. So, I
Okay.
mean, yeah, I'll discuss after the quiz. Like, uh, yeah, the reductions things is a bit, like a bit, maybe I would say a bit shaky, so to say. But
Okay.
I'll follow it up after the quiz. Yeah.
Okay. Sure. Yeah. Remember directionality, equivalence, polynomial time. Those are the three main
Yeah, I
things.
mean the
Right.
material is clear, but of course,
Yeah.
when a new
Yeah.
question comes in, then
Yeah. Then
it's
I
a
think
bit, yeah, yeah.
right. Yeah, that's just really a matter of time and practice. So don't worry about it at all. So cool. All right. So Prashant and Manisha, do you have any other questions, or
No, no,
was
ma'am,
this
not
okay?
from.
Okay. All
Thank you.
right. Sounds good. All right. Thanks so much, everyone, for joining and also staying back all the way till the end. All the best with the quiz and all the best with anything else that's coming up in your other courses, any other deadlines, and so on. I really appreciate having a chance to meet you ahead of the quiz. And take care, good luck, and we'll meet again in the next live session next week. Yeah? All
Thank you.
right. Okay. Thanks so much. Bye for now. Good
Thank
night.
you, ma'am. Yeah.
All right. Cheers. Bye. Okay. So is the live streaming stopped now?